Yeah, I'll just remind you the thing that we had been covering was FIR filter design. And we had gone to the stage where basically you start with a desired filter. So what you are given is HT of n or HD of n for desired. And it has a frequency response HD of e to the j omega. We talked about these kinds of filters are infinite impulse response. They can't be represented using constant coefficient difference equations. So the right thing to do is you basically truncate this filter or window this filter. So we ended up with the statement that turn it into an FIR filter by multiplying it with a rectangular window. And we talked about the window. Some people write that window in a causal manner. Some people write it in a non-causal manner. So this is 1 for 0 and n minus 1 and 0 otherwise. So what you get is basically you get your filter HTN that is multiplied, this rectangular window is multiplied by a time shifted version of your desired frequency response. So where m is equal to n minus 1 divided by 2. So this way you get a causal filter, and we started looking at what is the effect of this on the desired frequency response. So you want a desired frequency response. For example, your frequency response could have been HD of e to the j omega is, let's say, you have this cutoff. It's an ideal low pass filter. And in most filter specification cases, you only actually look at from 0 to pi region. So I'm not drawing the negative frequencies. So this is your desired frequency response. And then we looked at basically in the frequency domain, this multiplication gives rise to periodic convolution. And because of the convolution, what the response that you get is actually that you get these ripples. And then, so you have some transition width. You don't go from 0 to 1 or 1 to 0 in one single instant. It takes you a while to go down or go up, depending upon whether you have a low pass or a high pass filter. And then in the pass band and the stop band, you have certain ripples. Okay, so these things are described by, we looked at the case that this Wn has a Fourier transform W of e to the j omega. So this is the Fourier transform of the window. And we looked at the Fourier transform, for example, rectangular window. If you look at it in terms of just the amplitude, it looks like this. So it has the sine over sine form. It looks like a sink, but of course it can't be a sink because it has to be periodic. So this width, we call this part the main lobe of the window, when it's actually, the right term is it's main lobe of the frequency response of the window. Okay. This main lobe width basically causes the transition from pass band to stop band. So that amount of time it takes your frequency response to go from 1 to 0 or 0 to 1, that is proportional to your main lobe width. And then the amounts of ripples that we see, we talked about those ripples are proportional to the ratio of the main lobe height to the side lobe height. Okay. So we talked about transition width. That's proportional to main lobe width. And the ripples, they are proportional to peak side lobe height divided by the main lobe height. Now, we talked about for the rectangular window, we talked about that the main lobe width for rectangular window, that is proportional to, so the main lobe width is actually exactly equal to the transition width is proportional to, but the main lobe width is exactly equal to 4 pi over n, or 4 pi over 2m plus 1, which is the definition of m. So the longer your filter length is, the narrower your main lobe width is, which means the sharper your transition is from 1 to 0 or 0 to 1. Whereas the ripples, so the peak side lobe height divided by the main lobe height, that for the rectangular window is equal to 13.3 dBs, and it is a constant. It is not a function of the length of your window. We related it to the Gibbs phenomenon. And this gives rise to the ripples have a size of approximately 21 dB. So we went over the FDA tool and looked at some examples of this phenomenon. This is just a recap of the things that we have already seen in our last lecture. Now, based upon this, what I want to talk about is that in practical filter design, because of the fact that you have this main lobe width which is non-negligible, and you have this peak side lobe height over main lobe height, because of this, there are some aspects that we need to be aware of when we are doing practical FIR filter design. So practical filter specification criteria. The first thing is we cannot have abrupt transitions from, let's say, 1 to 0 in the case of low pass filter. Okay. At frequencies, say omega c. Okay. And this is due to the main lobe width. Of the Fourier transform of the window. And the other specification is that we have oscillations or ripples in the pass band. So pass band is where you are supposed to have exactly one or some other value, that's called the pass band, and stop band where you want it to be exactly equal to 0. Okay. So when you are talking about filter specifications, basically, let's say an ideal filter, an ideal low pass filter will have one cutoff. Say you are asked to design a filter with omega c equal to 0.3 pi radians. In reality, what you will be given is that there is a pass band and a stop band and a transition width. So instead of giving you omega c, people will say the pass band ends at omega p equal to, let's say, 0.25 pi. So a little bit before the cutoff. And a stop band starts at omega s equal to 0.35 pi. So what people are saying is that you are given a width of 0.1 pi to go from 1 to 0. Okay, and typically if you want to, how do you define the cutoff of such a filter? The typical definition that is used is you just take the average of the pass band and the stop band. So you do omega p plus omega s over 2, which in this case will be 0.3 pi. So that is what people will give you. And the other thing that people will tell you is that we want oscillations no more than delta in the delta p in pass band and delta s in stop band. So what that means is that you basically say in the, if this is your filter design, this is your omega p, the specification says that you don't want this response to be more than 1 plus delta and 1 minus delta p. So you want to stay within 1 plus delta p and 1 minus delta p. Similarly, at after omega s, you want to be within delta s. Okay? So these are the ripples that you are allowed. This is the window in which you can go up and down, but you shouldn't go beyond these values. And sometimes these dashed red lines that I have drawn, they are called the spectral mask. Now, for the case of FIR filters obtained, for FIR filters obtained using the window method, delta P and delta S, they always end up being equal. Whatever is the max deviation from one in the pass band is the same as whatever is the max deviation in the stop band. So delta P equal to delta S is given by delta. So for rectangular window, we already saw what we are allowed. Rectangular window basically allows the delta. In rectangular window, your delta cannot be smaller than what in dBs. So these ripples are, the max ripple is what gives rise to your value of delta. Okay, a rectangular window gives you a ripple of up to 21 dBs. You can convert that to linear scale if you want. Okay, so for a rectangular window, if someone says I want delta of, let's say, 50 dBs, they cannot achieve that. But if they say they want delta of, let's say, 15 dBs, they will achieve that, because in rectangular window, these ripples are always, this delta is always of the same value. Okay. So for rectangular window, this delta cannot exceed 21 dBs. Okay. So this is just a demonstration of what I just talked about earlier, the plot I showed you. This is for the low pass filter. I want you to be aware that the same statements could be talked about for high pass filter, in which case the stop band and the pass band definition will change. Basically, anywhere where your filter is supposed to stay away from 0 is called a pass band, and anywhere where it is supposed to stay close to 0 is called the stop band. And in general, you want your filter response, so this is 1. This point is 1. Your ideal filter was like this. Your ideal filter should have gone to 0, but you cannot draw this once you do the windowing operation. And so what you say is that this maximum distance delta, this is no more than some dB value, and in your stop band you want this to be no more than some delta S. Now for FIR filter design, delta S and delta P, it ends up being the same. So let's go back to the FDA tool and I'll try to walk you through it. So I'm going to talk about an FIR filter design. We are only interested in the window method, so let's select the window method. We'll talk about this other Kaiser window later. Let's talk about normalized frequency. So if you just leave the Kaiser window there, what this toolbox asks you is, where does your pass band end, which is this value? Okay, and this is of course in dB, so this is starting at 0 dBs. So it says, where does your pass band end? And I'll say 0.25 pi. Okay, and it says, where does your stop band start? And between that is the transition width. So I'll say 0.35. And then it is asking you, how many fluctuations are you willing to allow in the pass band and the stop band? Now, I'll just go to the linear scale. You can give linear scale or you can give dB scale, that's fine. I'll just do the linear scale. So let's say you want it to be 0.01 in the pass band and 0.001 in the stop band. Okay. And then you press design filter, and this is what you get. 0.01, whatever the value comes up. Let's go to the dB scale, just to stay consistent with the magnitude response. So we said the stop band should be 80, and the pass band should be 1 dB, no more than 1 dB. So you are allowing these fluctuations to be no more than 1 dB, and these fluctuations to be no more than 80 dBs. Okay. Now for FIR filter design, I can change, for example, let's change this to the pass band range to 20. And I press this, and you see no effect happening on the plot. The reason is that in FIR filter design, the pass band and the stop band ripples, their values are exactly the same. So when you tell your tool to give you a stop band ripples of 80 dB attenuation and the passband ripples of 20 dB attenuation. Since 80 dB attenuation is a more stringent requirement, it imposes the 80 dBs to both the passband and the stop band. Okay, so this is positive value, but it's talking about attenuation. It's in dBs. If I just talk about linear, for example, 0.001, I want the ripples to be no more large than 0.001 in the stop band, and in the pass band I don't want them to be larger than 0.01. Since 0.001 is a more stringent requirement, it just picks that requirement. Okay. On the other hand, if I made the pass band requirement to be, let's say, 0.001, you see that the stop band sort of goes down also, because now my passband requirement is the one that it selects for both the values. Okay, just do that again. 0.01, right? It's minus 60 dB because it has picked 0.0001. And if I do now 0.0001, then even though I have not changed the stop band, the requirement is the ripple shouldn't be bigger than that, but they can of course be smaller. And in FIR filter design, the ripples in passband and stop band, they have to be, in the window method, they have to be of the same height. So when I do that, it has to actually, it ends up affecting the stop band also. Okay, so now we understand how to relate the rectangular window design to what effects it has in the real filter frequency response. And what we have learned is that if we want the transition width to be smaller, we can keep on increasing the length of the filter. We saw that those exercises were done in the last class. You make the length larger, you will see the transition from 0 to 1 getting smaller and smaller. Okay, but let's say that someone comes and says that I want the attenuation, like the example that I did earlier, right? We saw that we were allowing the ripples to be no more than 80 dBs in attenuation. So earlier in the FDA tool example, we wanted, for example, delta P equal to delta S equal to 80 dBs. So when it's talking about attenuation, I'm going to skip the negative sign because we are talking about attenuation. Okay. But for a rectangular window, we know we cannot exceed 21 dBs. No matter what I do, I cannot get a plot where the ripples are attenuated by 80 dBs. So what that means is that we need a different kind of a window than the rectangular window. Okay, so a rectangular window, as the name implies, WN looks like the following. It's just a rectangle from 0 to n minus 1. And the reason it has strong ripples, it has large ripples, so 21 dBs, its ripples are pretty large, they only attenuate by 21 dBs, is because in time domain, it abruptly goes from 0 to 1. So if we want to achieve larger ripples, what we have to do is go to windows that more smoothly go from 0 to 1. The windows still have to be non-zero only from the range 0 to n minus 1, so that our FIR filter has only length n. But we want them to now more smoothly go to 0 or come from 0 to 1. Okay, so there are many different types of windows. The more common ones are, the first one is called the Bartlett, or it's also called triangular window. So the triangular window, I'm going to not shift it right now. I'm just going to write it in the unshifted version, Wn equal to 1 minus the absolute value of n over m plus 1 for minus m less than or equal to n less than or equal to m. So what this window looks like is the following. It has this triangular shape. It hits 0. And as you can see that unlike the rectangular window, this window is starting from 0 and going to 1 in a very smooth fashion. There is not an abrupt change. And that allows us to have a larger side lobe attenuation. We'll look at those values later. Then another window that we have is, so these windows have these names because of their inventors or people who proposed them. The next one is the Hahn window. So that is Wn equal to 1/2 1 plus cosine of pi n over m. For m, again, I'm not making it causal. It's only going from minus m to m. The other one is the Hamming window. That is Wn. So it's very similar to the Hahn window, but there is some change. Cosine of pi n over m. So if you compare the two, basically Hahn window uses 0.5 for both the terms, whereas Hamming window uses 0.54 in the first and the 0.46 in the second term. And the last one, which is a particular window, is Blackman window. Wn equal to 0.42 plus 0.5 cosine of pi n over m plus 0.08 cosine of 2 pi n over m minus m less than or equal to n is less than or equal to m. Okay. So let's look at what do these windows look like. So here is a plot of different windows where the plots are drawing the envelopes. They are not showing you the stem plots. So if you want to calculate the stem plots, you just create the stem values like this. You will have values going like this and so forth. So you see they are all very similar to each other. The rectangular window is the most different from all the other windows. The rectangular window goes from 0 to 1 and 1 to 0 very abruptly. All the other windows are starting from 0, smoothly go to 1, and then come back to 0. And because of this, the smooth transitions allow the other windows to have really small values of delta. Okay. So if I tell you I'm interested in the ripple delta being 15 dB, go ahead and use a rectangular window. But if I tell you I am interested in having delta to be 30 dBs. Okay, so it's attenuation, which means the larger number is smaller value. Okay, so if I'm interested in delta equal to 30 dBs, then I must use another window. I cannot use a rectangular window. Now, the question is, if we have other windows that give us smaller values of delta, should we ever be using rectangular window, or is there some sort of a free lunch that we can just ignore about the rectangular window? And the answer is no. So these windows give us smaller delta in linear scale. Whenever I'm talking about smaller, I'm talking about in linear scale. But this is not free. It is at the expense of larger main lobe width. So remember, what does the main lobe width affect in terms of the filter design? So if the main lobe width is large, that means that for the same filter length, it takes the filter longer to go from 0 to 1, even though its side lobes are now very attenuated. The ripples are small, but it takes it longer for the same window length to go to from 0 to 1 or 1 to 0. So here is a table that you can refer to for figuring out how different windows behave. Okay, if you want to just look at, so this is related to your transition width, and this is related to the size of the ripple or maximum ripple. Okay, so this is in dB scale 20 log 10 delta. Okay, and what this is saying is, so a rectangular window, if you go down this column, what do you see? For the same length, so m, remember m is n minus 1 divided by 2, right? So m is directly proportional to the length of your filter. So if you look down in this column, what it shows is that rectangular window for a given length has the smallest main lobe width, which means it has the smallest transition. So if someone says, I cannot have you do more than 64 length filter, then the filter that will have the smallest transition will be a filter made using the rectangular window. If you go to Bartlett, Hahn, and Hamming, they have the same transition width. Okay, these three have the same transition width, and then Blackman has the next. So if you look at it, what you see is that in terms of transition width for the same length of the filter, okay, Bartlett slash Hahn slash Hamming is roughly twice. It's roughly because instead of the divisor is not m plus 1, it's m. So it's approximately twice the rectangular window. And for Blackman, it is thrice the rectangular window. Okay, or if you want to flip it, if you want to use the same transition width, but you want to use a Blackman window, the length of your filter has to be 3 times the length of your rectangular windowed filter. Okay, And the longer the length of the filter, of course, the more memory you need and the more computations you require. So that's the trade-off. But now let's look at the approximation error. So this is the column that gives you the approximation error, which gives you the ripple size. So which window has the smallest ripple? Rectangular window. After that, Bartlett has 25 dB attenuation. Hahn has 44 dB attenuation. Hamming has 53 dB attenuation. And then Blackman has 74 dB attenuation. So let's say someone comes to you and says, I want to design a filter where I have this requirement for transition width, but I want my ripples to be no larger than 60 dBs. So if you want your ripples to be no larger than 60 dBs, they must be attenuated by at least 60 dBs, which is the only window you can use. The only window in that case that you can use is the Blackman window, because every other window has an attenuation of less than 60 dBs, and no matter what length you use, you cannot change the attenuation, this delta, for these windows. So basically, when someone comes and tells you, this is my transition width and this is my delta requirement, the first thing you do is pick the window based upon your delta requirement. Then you fix the delta requirement. Now you have fixed the window, and now you pick the length of the filter based upon what is the transition width that you are interested in. Now, one more thing that I want to point out, look at these boxed versions. What do we see? All three of these windows have the same transition width, but they have different attenuations. It doesn't mean that all these three windows will give you the same frequency response or shape, but the attenuation is different from the three windows. Their transition width is the same. If you had to pick among these three boxed windows, Bartlett, Hahn, and Hamming, what will be a natural choice that you should only pick one of these windows and just never use the other two? So the window you want to pick is always the Hamming window, because this window has the largest attenuation and it has the same main lobe width as Bartlett and Hahn. So in reality, the three windows that you should look at for design is rectangular, Hamming, and Blackman. And how you should pick them? So choice of window, first look at which window satisfies the delta requirement. Based upon that, you pick the window. So if your delta is, for example, 15 dBs, there is no reason to pick Hamming or Blackman because of the transition width. But if your delta requirement is, let's say, 40 dBs, then you will pick Hamming window. If your delta requirement is 55 dBs or 60 dBs, you will pick Blackman. What if your delta requirement is 80 dBs? So if your delta requirement is more than minus 74 dBs, you are not going to pick any one of them. None of these windows will satisfy, and then we need to look at other windows. So we'll come to that. But once you pick a window based upon your delta requirement, then we decide the length based upon the transition width. Okay, so let's come to, again, the FDA tool. I'm now going to work with high pass just to tell you that there is no difference in this discussion between high pass and low pass. We use just low pass filter as an example. Okay, I go to FIR filter, pick the window, and if you go now and pick the window, you see you have all these different types of windows. Okay, I don't want to, and you can indeed give a user-defined window. Okay? You can come up with your own window and give that window in this toolbox. But we'll just stick with the ones that we know. So rectangular window, I'm going to say I have a cutoff of 0.6 pi, and then you tell it the order that you are interested in. So order is just length -1. So let's do a filter of length 11. This is what I get, right? We looked at it. Our cutoff is 0.6 pi. And if you sort of look at it, you are going from 0 to this is your -20 dBs. It takes you about a distance of 0.2 pi. Okay? And the height is, the maximum ripple size is about -21 dBs. You can change the length as we did last time as much as you want. It's not going to affect the maximum ripple. The other ripples will go down, but the maximum ripple is not going to go down. But let's change it to 20, and what we expect is that the transition will get closer to 0.6. So let's do it, and I do this 20. I see some ripples here. The transition width has shrunk by a factor of 2. Instead of 0.2 pi, I'm now transitioning in 0.1 pi radians. But you see the maximum ripple size is still -21 dBs. Okay? Now let's go to, we talked about, we'll just focus on 3. So let's go to Hamming. Okay? Remember, the Hamming is about -53 dBs attenuation. So what we expect is that this ripple from -21, this will go to actually -53 dB. But what will happen, I haven't changed the length of the filter. What will happen to this transition width? It will expand by a factor of 2. Okay, so let's do that. And you see that I have about, this is, now the shape looks very different. I have about this -53 dBs around here. Okay, but look at this, this number has really gone down. It was -21 dBs, it was here. And that's why this looks almost flat, because the ripples in the passband are now, instead of -21 dB, they are -53 dB. So it almost looks flat to you. Okay? But look at the transition width. It has gone down. It has expanded. If I want to get the same transition width as rectangular, I must increase the length by a factor of 2. I need to make this 20, 40. If I do that, I've shrunk the transition width. Okay. Now let's go back to Blackman. So Blackman is about, if I remember, it was -74 dBs. I'll go back to the order of 20 to compare it with rectangular window. So I'm going to get now this peak amplitude down to -74 dBs. It will go down even further. This passband will look even more straight. But what is the effect that is going to have? The transition is now going to become 3 times. So now you will go from stop band to pass band. It will take you 3 times as much as the rectangular window. So let's do that. Here is the Blackman window. I press design filter and you see that this has really gone down, but look at the amount of transition that it's taking it. Okay. Now I increase the length by a factor of 3 to get down to the same width that I wanted for my rectangular window. Okay. And now this is what I get now compared to the rectangular window. So among these predefined windows, you can go to better windows to get a lower, to get a better attenuation, or to get smaller sized ripples, but the price you have to pay is in terms of the transition width, which means if you want to get the same transition width, you need to increase the length of your filter by a certain amount. I'd like to conclude the discussion of window-based FIR filter design by talking about basically adjustable windows. So as we saw earlier, all the windows that were listed in the table, they have one parameter only. They are a function of the length. As you increase the length, their transition width or main lobe width decreases, but their attenuation stays constant. So these adjustable windows are basically windows that change shape to obtain the desired delta and since they change shape, unlike the previous windows, they must have an additional parameter. So by definition, these windows have additional parameters. Additional parameters. Okay. The two most famous ones, the two most common windows. So the first one is called the Chebyshev window. And I'm not going to write down the formulas for these windows because they are a little bit complicated. They are in your text. You can refer to those. But the extra parameter in this window is the side lobe attenuation. In dB or linear scale. So you give it how much side lobe attenuation of the window you want. Okay, it's the side lobe attenuation of the window you want, and based upon that, it gives you a different shape of the window that you can use for designing. The other window is called the Kaiser window. It has an extra parameter which is referred to as beta. And this parameter basically it involves both the main lobe transition, the transition width or the main lobe width, and the attenuation factor. And the formulas are available, which basically lets you know that if you are interested in this much attenuation, for example, let's say minus 90 dBs, you should pick a certain value of beta. Now, in FDA tool, it can automatically pick the right beta to match your specifications. So if we come back to our FDA tool, I can, for example, in here, the Chebyshev window is simply given by the Chebyshev. Okay, and as you see, it is asking for an additional parameter. It's saying what is the side lobe attenuation that you want. So, and that is in dBs. So I can say I want 80 side lobe attenuation, and it goes there. Right? Now this 80 is the side lobe attenuation of the window. Okay, it's not the attenuation of the ripples. And we know that the ripple size is proportional to the attenuation of the window, but it's not exactly equal to. So it's a little bit, you have to be aware of how to do the transformation. Kaiser window, at least in this toolbox, so here is the Kaiser window. It's asking for the parameter beta. Okay. And if I design, so one option is I specify the order, and in that case, I really need to know my relationship of beta to the attenuation and the transition width. The other option is I simply select minimum order. What that toolbox does with minimum order is it automatically calculates those formulas for you and gives you give the specifications in this region. You say, I want my stop band to be, let's say, 0.4 to 0.5. You say, I want my attenuation to be, let's say, minus 90 dBs. Okay? Which is no other window. Blackman, for example, only goes up to minus 74 dB. So you can say, I want 90 dBs. And if you say minimum order, it will automatically generate the right length and the right value of beta for you to use. So if I say design filter, if you come here, it has automatically selected an order of 116. Okay, so this is where it says it's 116, and you see that it's matching minus 90 dBs here. Okay, and if I increase that, I make it 100, it will have to, just by the general principle, I want the attenuation lower, but I haven't changed the transition width. So the Kaiser window that you get, it will change the value of beta, but it will also have to increase the length, because if it doesn't increase the length, it cannot match the transition width. So if I press this, pay attention to the order number here. I do that, and you see that the order has increased from 116 to 130, so that it can go in that transition that you have specified. Okay, so I'm not going to go into further details of Kaiser window or what's the relationship of beta to the parameters. You can read in the text. There are other computer algorithmic means of designing FIR filters with desired specs. One is called the equiripples design or Parks-McClellan algorithm. Most of these designs are really easy using basically MATLAB. They don't involve any equations that you can just simply solve. They involve some sort of optimization. So that concludes our discussion of the FIR window design method. In the next class, we'll start talking about IIR filters.